Hello everybody and welcome back to Calc 3 online. I just want to start and go through a few of these kind of dot and slash cross product relationships and make sure that we kind of know when to spot things that don't make sense and when some of them actually could make sense. So the first one, right, the main thing here is to know that like if you are doing a cross product, right, this is going to create a vector, whereas dot product will create what we call a scalar, or just a number. So if you have something like A dot B cross C, then that's okay. That's going to be fine because it's basically like A dotted with some other vector, which is just some like number, scalar, which is fine. There's nothing wrong about that. If you keep that in mind, you kind of think, well, what if I change it to a cross product, like A cross B cross C? You could do that. You could do A cross, this B cross C would give you some vector V. And then if you do a cross product there, you're just going to get some, I don't know, we're going to call it U. But that's also okay. There's nothing wrong about that. But this last one doesn't make sense because you would do the dot products first, and basically this is just like a number, and then it's saying what do you get if you cross that with another number, which just doesn't make sense. Like if you go to the cross product kind of determinant here, and you have these 6 blanks you got to put in. This is supposed to go here, and this is supposed to go here. And you should just be like confused, like it doesn't make sense. You can't do that. So definitely look at the order in which things are done, because sometimes you'll see, something like this that doesn't actually make sense. So what I really want to talk about today is a geometric connection between the cross product that was mentioned in those videos, but I kind of want to just give a little more I want to sell you, I guess, on this idea a little bit more. So this is a very important relationship. We had a cosine kind of formula before where we involved the dot product, right? That the dot product of like two vectors over their respective magnitudes was the cosine of the angle between them. In here, the magnitude of the cross product between two vectors is the magnitude of one times the other times the sine of the angle between them. And I just want to sort of show you why this is happening. I mean, basically, the way I look at this is it's really like a base times height kind of formula. And I guess it's sort of out of order based on my picture here. So the base is really like the magnitude of B part, and the height is the magnitude of A times the sine of the angle between, which you can see over here. So if you think of some geometry, this area of this parallelogram is just literally base, the length of that times the height, right? And so, this is just magnitude of that vector B. And then you can get this just using a little bit of trig, right? The sine of this angle would be this over this, right? So if you rearrange that, right, you can get that the height of this parallelogram would be magnitude of A times sine of theta. So really when I look at that, I just see it as base times height. And I see that part being the base and that being the height. And the stuff down here is really just kind of giving you, I guess, I'm thinking of it as like a little step-by-step diagram to kind of see why it really is the area of the parallelogram and also where the determinant comes in. So let me try to explain this a bit here. So let's label this B1. I'm going to call that B2. I'm going to call this A1. I'm going to call that A2. And if I was to find the area of this, okay, just the shaded part right here, right? It would be, I could do the big rectangle, right? A1, B2 minus A2, B2, right? And if you think of the determinant of these two vectors, so A1, A2, B1, B2, the determinant is actually A1, B2 minus A2, B1, right? So there's something going on with the determinant of the two vectors. And it's easier, I think, to see it when I split it up this way, but really this shaded area is the same as just the parallelogram formed by these two vectors. So this right here is exactly that vector, and this vector over here is this vector right here. And if you kind of break it up in two parts, I think it's easier to see. So let's see if I can kind of shade this better. So this right here, that region is going to be the same as this region in here. And this region here will be the same as this region, right? So if I wanted to break this shaded area up and just kind of rearrange it but have the same space, I could fill in that little rectangle down there. Then if I take, we'll do this color. So if I take that region and that region, they're the same. And if I take that kind of weird triangular region and that triangular region, they're actually the same. So I could kind of remove this, and I could get that last region right there. So really, this determinant is actually representing the area formed by this parallelogram. And if you take the magnitude of that cross product, it is going to give you that area. And it really just comes out of like geometry related to base times height for a parallelogram. So if you have that in mind, you can do some problems kind of in your head. So if you just use like a geometric idea and you want to find the magnitude of I cross J, I can just do this just without even doing a cross product. I have I down here, let's say, and I have J here. We know that they are length 1, so basically this is a 1 by 1 rectangle right here. And so without doing any computation at all, you could just know that that should be 1. The magnitude of that. I mean, you could do it out. You can do I, J, K. You could do 1, 0, 0, 0, 1, 0. And if you do that out and you get the vector, it's going to have, it's really going to be K. But if you then take the magnitude of K, it really is just going to be 1, which we know it's a unit vector. But it's good to see it in a picture like this one, just using kind of what we talked about. And kind of along the same lines, if you have a statement like A cross B equaling 0, it tells you something really important about those vectors. So what I want you to think about here is that basically this says there's no area between in the parallelogram that's formed by those vectors. And the only way that there's no area, right, because as soon as you have A and B moves a little bit off, there's going to be some, I didn't give myself enough room, but there's some sort of parallelogram there. But if there's no area at all, then basically it means that let's say that's A, then B is in line with A, or B. So either A is in line with B or B is in line with A, whichever way you want to say it. So you could say like vector A is just some scalar of vector B. That means that those things have to be parallelogram. It's a common like test to kind of see if vectors are parallel. You can take their cross product, and if you get anything that's not zero, then that means they're doing something kind of like this up here, where they're going to make some sort of parallelogram that has some sort of area. So this is just a good example of how you can use what we've been talking about to, like you can use the magnitude of the cross product to calculate some area. So if you have 3 points, so we got P, let's say is right here, we got Q, let's say is down here, and we got R right here, right? I want to know the area of the triangle in three-dimensional space formed between them. And it's much easier if you just kind of use the parallelogram, okay? So if you instead think about this parallelogram, okay? If we found the area of that parallelogram and then just divided it by 2, we would have the area of that triangle that I want. And so you can basically solve a magnitude of a cross product problem and then just divide by 2 to do this. So I'm going to get vector PQ, which is just Q minus P, which is going to be, let's see, and then we're going to do P R, I guess. It doesn't really matter which ones you pick. We're going to get 0, we're going to get negative 5, we're going to get negative 5. And so that's these vectors, PQ, PR, right? And if I just take their cross product, I would have, let's do it like this, I, J, K, negative 3, 1, negative 7, 0, negative 5, negative 5. So take that determinant. If you do that out, you should get the vector negative 40, negative 15, 15. And then if you just take the, so basically the area of the red triangle would be the magnitude of that cross product, PQ cross PR, divided by 2, right? And so if you just do the square root of 40 squared plus 15 squared plus 15 squared all over 2, I'm just using a calculator. You get 5 halves times root 82. And that's it. That should be the area of this red triangle, because we divided by 2. Magnitude of the cross product will get you the area of the parallelogram. So if you chop it in half, you get the red triangle. So the last thing I just wanted to talk about was kind of an extension of this to 3 dimensions. So this is something called the scalar triple product. And if you kind of think about the first thing we talked about, this does make sense. You can do this, right? This is a vector, B cross C, and you can dot that vector with another vector. So this right here is a number, right? It's a scalar. And that scalar actually represents the signed area of, it's a very funny word, but the parallelepiped formed by those vectors. So the parallelepiped is like this higher dimensional analog of a parallelogram. A lot of times we add weird endings like this to make it a 3D thing. So you've got the parallel pipette, which is formed by A, B, and C, those vectors. And if you actually just do B cross C dotted with A, that number, it represents the signed area of the volume, signed volume, that's what I want to say, of that parallelepiped. And to kind of make a connection back to what we just talked about, really, like, if you want the true distance, you would take like the absolute value of this, which a lot of times in application problems is what's more important. And when we do things like absolute value of -5 and we get 5 or something, the absolute value is really just the scalar version of magnitude. So we could take like the magnitude of a vector. It's just the double bars are actually, the notation is built off of the absolute value bars that you're used to. So when we see magnitude symbol like this, basically think of it as taking the absolute value of a number. It's just like the absolute value of a higher dimensional number, which is really what a vector is. It's just like a higher dimensional analog of a scalar like that. But yeah, this thing, just like kind of an integral, gives you signed area under a curve. This thing would give you signed volume of a parallelepiped.